Adam from RFOXiA from our real lab. Today we're answering, does your autonomous system actually know where it is, and can it tell anyone about it beyond line of sight? If you are building an autonomous robot or a drone that is supposed to make decisions on its own, there are two things it needs to do. It needs to know where it is, and something, a ground station, a controller, another node, needs to know where it is too. These sound like the same problem. They are not. They are two separate engineering problems that most systems solve separately, with separate hardware, separate power budgets, separate failure modes. The Multinav Pro Plus Belly module paired with the GNSS module solves both of them in one unified ecosystem, so your robot actually knows where it is and where it needs to go. Let me start with the GNSS side, because the numbers here are worth understanding properly. Consumer GPS modules, the ones you find in most maker kits, most drone flight controllers, most off-the-shelf tracking hardware, typically update at 1 Hz to 10 Hz. 1 to 10 position fixes per second. For a drone flying at 15 meters per second, a 1 Hz update rate means the system is making navigation decisions based on a position that is already 15 meters stale. That is not a rounding error, that is a navigation problem. The GNSS module in the RFOXiA ecosystem runs at 18 Hz, 18 position fixes per second. At that same drone speed, the maximum positional staleness between updates is about 83 centimeters. That is a fundamentally different operating condition for any autonomous decision system. The accuracy figure is 1.5 meters. That number does not come from ideal conditions in a clear field with perfect satellite geometry. It represents what the module delivers in real deployment scenarios. For most autonomous systems, 1.5 meters is the threshold below which navigation becomes genuinely useful. Above that, you are compensating for error. Below it, you are actually navigating. Now to the BLE side, and specifically to why this module achieves ranges that no commodity Bluetooth hardware gets anywhere close to. The wireless industry spent years obsessing over transmit power. The assumption was that range is a function of how loud the signal is. If you want more range, you amplify. That logic has a ceiling. Regulatory limits cap transmit power. Beyond a certain point, amplification adds heat, adds current draw, adds regulatory complexity, and still does not solve the real constraint. The real constraint is on the receiver side. Specifically, it is receiver sensitivity, the ability to detect and decode the weakest signal that physics will actually deliver to the antenna. The BLE module in this ecosystem uses a chip with -104 dBm receiver sensitivity. To put that in practical terms, that is the ability to hear a signal that is 10 trillion times weaker than 1 milliwatt. Most commodity BLE chips operate at around -90 to -96 dBm. That difference of 8 to 14 dB corresponds in free space link budget terms to roughly a factor of 2.5 to 5 times in range before you have done anything else. Combine that sensitivity floor with an optimized RF front end and a proper antenna, and you get to the range figures this module actually delivers. 5 kilometers ground to ground, where both modules are paired with smartphones at ground level. 15 to 20 kilometers man to drone, where one module is at ground level and the other is elevated on the aircraft, eliminating most of the multipath reflection losses. 50 kilometers drone to drone, where both modules are airborne and the ground reflection problem essentially disappears. This is not amplification. The transmit power is within unlicensed Bluetooth spectrum limits. This is receiver engineering. Now consider what happens when you pair these two modules in an actual autonomous system deployment. The GNSS module is generating a verified position fix 18 times per second to 1.5 meter accuracy. That data, latitude, longitude, altitude, velocity vector, needs to go somewhere useful. In a conventional setup, it goes to an onboard flight controller that does local processing with a separate telemetry radio sending a slower, lower resolution stream back to a ground station. You have 2 radios, 2 power loads, 2 points of potential failure, and a telemetry stream that is almost always the bottleneck. In this ecosystem, the GNSS module feeds directly into the BLE module interface. The BLE module handles both the local processing and the long-range communication in one device. The ground station, which in this case can be a smartphone running the RFOXiA Connect app, receives real-time GPS position overlaid on a live map, sensor data from the sensors module if that is also present, and full bidirectional control capability through the same link. No secondary telemetry radio, no secondary antenna, no secondary power draw. The 2 megabits per second data rate matters here. Most long-range telemetry systems operate at much lower data rates because they are trading bandwidth for range. The design philosophy here did not require that trade because the range problem was solved on the sensitivity side. You get the range and the bandwidth. That is what enables real-time 18 Hz position streaming over a 20-kilometer link without compression artifacts or dropped frames degrading the navigation picture. The application scenarios where this combination becomes genuinely useful are not exotic. Search and rescue operations where a drone needs to cover large areas and report precise position back to a ground team without relying on cellular coverage. Precision agriculture where robots need to navigate field boundaries to sub-2-meter accuracy and communicate status over farm-scale distances. Research deployments where you need high-resolution positional data and you need it reliably in locations that have no infrastructure. These are real use cases that currently require either expensive proprietary systems or uncomfortable. That is the engineering behind how these two modules work together. Now let me show you the actual hardware, starting with the BLE module itself. This is the range foundation of the entire system. At 50 kilometers drone to drone and 20 kilometers man to drone, the BLE module handles the communication half of the autonomous positioning problem, keeping the ground station fully informed at 2 megabits per second over distances most wireless hardware cannot reach. 2 megabits per second over long range is not something you typically get to choose. The BLE module delivers it because range was solved on the receiver sensitivity side, not by sacrificing bandwidth. That means your 18 Hz GNSS data stream arrives intact in real time without compression. The STM32WB07CCV6 runs the BLE stack and your application logic simultaneously on the same chip. When your drone is streaming GNSS position at 18 Hz and managing sensor data and responding to control inputs, this processing core is what keeps all of it synchronized without dropped packets or timing drift. 57 by 47 millimeters, that is the entire long-range wireless compute node. Corner mounting holes on a 51 by 39 mm frame. It fits in the same space envelope as modules that deliver a fraction of the range, and it integrates with the GNSS module directly through the onboard interface. The GNSS module connects through a dedicated interface on this board. So does the sensors module, the motor and battery management module. One unified platform means the 18 Hz position data, the environmental data, and the control link all run through one device, one power rail, one integration effort. The RFOXiA Connect app receives the GNSS position stream from this module and plots it on a live map in real time. You are watching your drone's actual 1.5-meter accurate position update 18 times per second on a phone screen over a 20-kilometer link without any internet infrastructure involved. When the communication link needs to be text or voice between operators rather than data to a ground station, the same hardware handles that too. Internet independent, range limited only by the same link budget that delivers 20 kilometers of drone telemetry. The firmware is yours to modify. Full open source access and SWD programmability means you can customize how the GNSS data is processed, how the communication protocol behaves, how the module responds to specific conditions. The hardware sets the ceiling, the firmware is what you build. The RTC crystal handles precise timing synchronization across the ecosystem. When you are correlating 18 Hz GNSS fixes with sensor timestamps and control inputs over a long-range link, timing drift compounds into navigational error, the integrated RTC keeps everything referenced to the same clock. The FCC certification on both modules is not a footnote. It is what makes this deployable in actual applications rather than just on a workbench. Certified hardware can be operated legally, can be integrated into commercial products, can be shipped internationally without recertification costs, and can be sold through distribution channels that require it. The engineering decisions that got this hardware to these specifications are one part of the story. The certification is what makes those specifications useful in the real world.